imagine a metal. It's used to build our most advanced jets, spacecraft, even the body armor that protects lives. But here's the twist. It's so unbelievably tough that actually shaping it is one of engineering's great puzzles. Today, we're going to crack the code of this super alloy.
The material we're talking about is a titanium alloy, officially known as Ti-6Al-4V. And this isn't just some run-of-the-mill metal. It is, quite literally, the backbone of some of our most critical technology, both here on Earth and way, way out in space.
And when I say critical, I mean it. Just look at this list. We're talking aircraft engines, naval ships, spacecraft, missile components, you name it. It's even used inside the human body for things like cranial implants. Basically, whenever you need something to be incredibly strong but also lightweight, this is the material you turn to, no question.
Okay, so if it's so amazing, what's the big deal? Well, there's a pretty major catch. For all its incredible uses, this stuff has one huge flaw. It absolutely hates being shaped.
And that brings us right to the heart of our story, the massive challenge this superalloy presents to anyone who tries to work with it. This chart lays it out perfectly. On the one side, you've got this dream list of pros. It's super strong, it's light, it doesn't corrode, and it can handle high temperatures. Amazing, right? But on the other side, you have these two massive cons. It's difficult to form and has what engineers call poor workability. You can't just stamp it into a shape like you would with steel. It'll fight back, it'll crack, it is just incredibly stubborn. So how in the world do you get around that? If you can't force it, you have to get clever. You need a method that can shape this ultra-strong metal almost gently, almost as if it were soft clay.
And that clever method is called Incremental Sheet Forming, or ISF. The magic word here is incremental. Instead of one giant brutal press, ISF uses a simple tool, guided by a computer, to slowly and carefully nudge the metal into the shape you want. It's incredibly precise, and you don't need these huge custom-built molds, which makes it perfect for creating really complex one-off parts.
It's actually pretty straightforward when you break it down. First, you clamp a thin sheet of the alloy into a frame. Then, you tell a CNC machine, basically a very smart robot, the exact path for its tool to follow. And finally, the tool just goes to work, moving along that path and pushing the metal bit by tiny bit until eventually the final part takes shape. Seriously, it's like watching a robotic potter at work, but with super strong titanium instead of clay. But, just having the technique isn't the whole story. To get a truly perfect part, you need a perfect recipe. And that's where the real investigation begins. This is the million-dollar question, isn't it? If you're going to use this incredible process, what are the exact optimal settings you need to dial in to get the absolute best result possible? Well, researchers figured there were three main dials they could turn. First, there's the tool's rotational speed, how fast it's spinning. Second, the step depth, how deep it pushes into the metal with each pass. And third, the feed rate, how fast the tool actually travels across the sheet. For their experiment, they tested each of these at 3 different levels. Now here's where it gets really tricky. They weren't just trying to make one thing better. They had all these competing goals. On one hand, they wanted to maximize the final wall thickness, which means more strength, and the wall angle for better accuracy. But at the exact same time, they needed to minimize surface roughness for a nice smooth finish and the amount of force the machine was using, which is all about efficiency. And here's the perfect example of that dilemma in action. Let's say you make the step depth deeper. The tool pushes harder. Great, the part gets made faster. But that also makes the walls thinner, which could make the part weaker. And it puts a ton more stress on the machine. See the problem? It's a constant balancing act. Improve one thing and you might make another thing worse. So, with all these different variables and these conflicting goals, how do you possibly find the single best combination? Well, you need a very special key to crack this optimization code. First things first, you need data, a lot of it. The researchers were incredibly methodical. They ran 20 completely unique experiments, tweaking the dials in different combinations just to see what would happen and to measure everything. Then, they took all of that data and fed it into something called Grey Relational Analysis. Don't worry about the name. Just think of it as a super smart analytical tool. Its job is to look at all the messy, conflicting results and find the one sweet spot, the single best combination that gives you the best possible outcome across all of those competing goals. So, after all the tests, after all the number crunching and the sophisticated analysis, they did it. The code was cracked. They had found the ultimate manufacturing recipe.
So what is it? After everything, what are the 3 magic numbers that give you the strongest, smoothest, most accurate part with the least amount of effort?
First up, the tool speed needs to be cranked all the way up, 200 revolutions per minute.
Next, the step depth needs to be the absolute shallowest they tested, a tiny, precise 0.1 millimeters.
And finally, the feed rate needs to be at maximum speed, 2,000 millimeters per minute.
And don't just take my word for it. The researchers themselves concluded, and I'm quoting here, that after running their multi-objective optimization, these settings were observed to be the optimum parameter settings. Plain and simple.
So what this recipe gives you is the perfect balance. A fast-spinning tool moving quickly across the surface but taking only tiny, gentle steps. That's the secret sauce. That's how you create the strongest, most accurate, and smoothest parts possible, all while being efficient. It's the best of all worlds.
And that leaves you with a really fascinating thought, doesn't it? If we can apply this kind of methodical analysis to find the absolute perfect formula for shaping a superalloy, what other incredibly complex systems in our world are just sitting there waiting for someone to finally crack their code?